Hello, gentle readers. Welcome to another episode of Logos 2000. Today, after the integrodiffer, the differintegro, that the differential and the integral are these key aspects of real analysis that are at once complementary yet disjoint, and yet that have in each of their closures in each other these great confluences of helping to explain why in the integral and differential analysis it's always a differential and integral analysis. These derivations of the quantities and the functions, the relations, so among them, that it becomes a more unified sort of theory to have real analysis for the integral equations and their plane curves, and the differential equations and their solutions, and of which there are many, that then among each other it helps to describe that there are these systems that altogether make for a fuller complement of the integrodiffer and differintegro. So the differential analysis is usually approached as that which arrives at scalar values and numbers. And the integral analysis is in the indefinite is what so arrives at areas and volumes or the parameterizations thereof. Yet it's not unreasonable, and in fact it becomes rather fundamental after a sort of deconstructive account for a greater structuralism again, as I have for it, that the integral analysis needs to have this sort of second course attachment to make it so that there's always this nominally non-zero term for a differential equation as of an integral equation as a differential equation, and then that may be practically or actually zero. Has that for most systems involving models of dynamical systems, where the entire idea that is all dynamical modeling has that the way to make this so has to start with sort of with Duhamel's principle and the attachment that has within the development of the formalisms after Cauchy and Weierstrass and Dirichlet and Poincaré, to get into the heart of the matter, as it were. That this way we can look to further explore the differintegro and the integrodiffer as a reflexive yet a thoroughly resounding system altogether. And this isn't necessarily just exactly about the fractional differentiation or the extraordinary systems, as they may so be, and nor is it necessarily so attached to what is called integrodiffer and differintegro, as with regards to things like the symplectic, and here's that's kind of framed with regards to Poincaré and completions. What that means is that it's got all the outsides as vis-a-vis just the scalar inner product, which results for the severe abstractions in this dimensionless analysis. That what it needs is more of a fuller dimensional analysis, and the means to formalize that the algebraic derivations of quantities can so be kept that thusly the higher order continuity is maintained of the systems so purported to be described, like physics and mechanics and all the things in the dynamical modeling. So as is pretty usual, it's just a matter of starting to begin at some given books here as stores of knowledge, kind of like Sagan put it one time. He's like, man might be a bright animal, but if he didn't have a library and read it, and then he wouldn't know much. And so that's kind of considered the store of value, the money, as it were, of the economy, as it were, of knowledge, scientific knowledge, technical knowledge, common wisdom, and all such related notions. So let's take a look and see what we find here today in the stacks. We left off reading a bit from this Cornelius Lanczos and the linear differential operators. And so what this intends to entail is that there's a great course of operator theory and the operator calculus. And so that gets into being able to treat functions as objects, and then dealing with the various notions that are opposites to each other, yet still arrive from that things are closed and complete yet infinitary. So when you talk about that an operation is closed, like an operation of arithmetic, and or an operation of algebra, those being not necessarily the same thing in terms of the numbers and the words, yet having a modular attachment in the middle. It has that the operator theory is sort of a high-level course, and it makes for lots of different ways to approach these things, to make algebraic derivations then thusly as vis-a-vis systems of equations or equations or inequalities, or otherwise what end up being the center of the diagram or the notation, and then that thusly those have all their parts and constituents and types and categories essentially. So in the preface here, Lanczos begins, as of this reprint from Lanczos that was printed by D. Van Nostrand in 1961, à la portrait de la humanité universelle, la père pire dont la charité ne connaît pas de limite. So that's kind of a nice way of saying that the infinite limit is the continuum limit. Preface. In one of the unfortunately lost comedies of Aristophanes, the voice of the mathematician appeared as it descended from a snow-capped mountain peak, pronouncing in a ponderous sing-song, in words to which the audience sounded like complete gibberish, his eternal theorems, lemmas, and corollaries. The laughter of the listeners was enhanced by the implication that in 50 years' time, another candidate of eternity would pronounce from the same snow-capped mountain peak exactly the same theorems, although in a modified but scarcely less ponderous and incomprehensible language. Since the days of antiquity, it has been the privilege of the mathematician to engrave his conclusions expressed in a rarefied and esoteric language upon the rocks of eternity. While this method is excellent for the codification of mathematical results, it is not so acceptable to the many addicts of mathematics. From the science of mathematics is not a logical game, but the language in which the physical universe speaks to us, and whose mastery is inevitable for the comprehension of natural phenomena. In his previous books, the author endeavored to establish a more discursive manner of presentation, in which the esoteric shorthand formulation of mathematical deductions and results was replaced by a more philosophic exposition, putting the emphasis on ideas and concepts and their mutual interrelations rather than on the mere manipulation of formulae. Our symbolic mechanism is eminently useful and powerful, but the danger is ever present that we become drowned in a language which has its well-defined grammatical rules, but eventually loses all content and becomes a nebulous sham. Hence the author's constant desire to penetrate below the manipulative surface and comprehend the hidden springs of mathematical equations. To the author's surprise, this method, which of course is not his monopoly, was well received and made many friends and few enemies. It is thus his hope that the present book, which is devoted to the fundamental aspects of the theory of linear differential operators, will likewise find its adherents. The book is written at advanced level, but does not require any specific knowledge which goes beyond the boundaries of the customary introductory courses, since the necessary tools of this subject are developed as the narration proceeds. Talks about algebra. Interpolation. The problem of attaining a function from a discrete set of values. That is the problem of interpolation. We investigate the properties of the Gregory, Newton, and Stirling type of interpolations. Second station is harmonic analysis. Here there's quite a discussion of harmonic analysis, where harmonic functions are merely defined to be those whose Laplacian is zero. Has that there's resonance theory above that, and so there's for the Gladney functions or Chladni functions and these type of things that the harmonic theory is kind of like differential theory when we're talking about the differintegro and integrodiffer. It's not by itself. It's part of a wider complement, and so it's similarly with harmonic theory. And then with interpolations, then there's kind of discussed interpolations or extrapolations. So that's usually part of what's called methods in the applied, particularly. Then as with regards to when those maintain or identify an outside that then is usually cumbersome and not very attractable, yet fully captures the character therein, vis-a-vis the inner scalar product, usually the dot product, a number that results to get out a number that results. And then as with regards to all the things that go into the linear and the unlinear and these kinds of things. We can hardly find a better introduction to those orthogonal expansions, which will play such a vital role in our latest studies, than by studying the nature of the Fourier series. As was mentioned here several times, it's so that given any kind of pair of orthogonal functions whose product together ends up being 0 or 1 according to like addition and multiplication, or any two given products, it's possible to find orthogonal functions as this pair of functions that has this property over a given bounds that has that it's 1 in one place and 0 in another place according to the operation. Because then the role of the operations can be used to define, and that gets in things like that 2 plus 2 equals 4, 2 times 2 equals 4, 2 squared equals 4. Why that makes so much so that for things like addition and multiplication and convolution, and really so much so for powers and roots in any sort of operation, that they're the ways to define then where they meet and where expressions of them meet. For example, as with regards to the golden ratio phi, that transcendental constant that's so evident all throughout nature, that 1 minus phi equals 1 over phi, that the one operation and the other operation happen to have their point where they're equal, make for so why phi is very very much visible in many places in the operator calculus and the operator analysis with regards to these operations and their operators and where they meet and these things with regards to the regular singular points 0, 1, and infinity of the hypergeometric, of course, and then as with regards to any of those as how they may so be, and that 2 is at once just the simplest next number after 1, but at the same time it's also in the middle of all these modular results, that all these transcendental results, as all and about them, happen to meet in the modular, meet in the middle, the arithmetic and algebra, the Cantor spaces, all these things have, whether they're built from the integers or whether they're built from the real, and that they are both, and that's one of the reasons mathematics' objects are so platonically ideal, is because they're always that way. That's great. And he says the third idea is matrix calculus. So this helps to establish that Lanczos is getting into this from the applied and making for systems of equations, and then the matrix calculus is a number of different things, just to do with it, taking beyond a left-hand side, right-hand side of an equation to either the coefficients of a related polynomial or any other kind of way to make that structurally, graphically, is according to a matrix with all the things that go into that, and that being rectangular, pretty much. And then as with regards to whether that really has the character that it can keep for the later the Hamiltonians and Hamiltonian Jacobi equations and these kinds of things, which are so part and parcel since Lagrange of the severe abstraction of mechanical reduction, that it's as well that this then makes a setting for the applied. But the operator theory and this being linear differential operators, but that there's any kind of things usually called part of functional analysis for operator theory, so function theory and operator theory. That Lanczos is here to describe that these are the three things that really set up all this stuff that goes into the operator calculus, which is, of course, very much part of real analysis and all such sorts of things. So taking a look here at this then, through the concept of the function space, we establish the link between matrices and the continuous domain. See, this just goes to show that there is a link between these discrete things in the continuous domain yet as well it's according to continuum mechanics most thoroughly. And then the modular that establishes all such matters of metric and norm. And then when he says the continuous domain, that just, we might read that as the sector of this analysis, vis-a-vis that a domain, as of a domain of a function, has the continuous domain here is defined, and that it's a particularly usual and central object of mathematics. And we proceed to the central problem of the Green's function. After Green, he was this a British analyst. After Newton and Gregory and Maclaurin and that, then there wasn't much change for a while in England. But then it went to France largely. But then Green kind of picked up and came up with some results in differential analysis that then make a lot of things tractable at a loss, as it were, of some of the generality. And he says, which, being the inverse operator of the Green's function, plays such a central role in the solution of differential equations. Certain elementary aspects of communication problems provide a number of interesting applications of the Green's function. Method in engineering problems. Once we proceed to the Sturm-Liouville problems, and here there was discussed at some length the idea of Heaviside and the telegrapher's equation. There's reading from Gonzalez Velasco of the Sturm-Liouville and the ideas that they have. And this is about when was introduced the notion that Duhamel's principle is kind of sitting in the middle of all that. Because there was the great kind of slide into simple, easier differential analysis, which is complicated, which is very thoroughly involved to get well defined in the sense of Hadamard, well posed and well defined, well behaved as systems of equations. That simply, accordingly, as not being complete, then it's not so that it would be expected that it would be so complete. And these are not unusual things, but then address the body of analysis. These are the usual things, which played such a remarkable role in the historical development of mathematical physics. In the chapter on boundary value problems, we get acquainted with the classical examples of the solution method known as the separation of variables, and then various matters of the substitution and resulting solvable or solved problems. But we add some highly non-traditional types of boundary value problems which bring the peculiar parasitic spectrum into appearance. So that would be an aspect of these things, the unlinear, is this sort of parasitic spectrum. And such notions that are these aspects of the otherwise failure modes are often given names like bad or ill or something like that, or here parasitic. But yet, reflecting on the spectrum, then there was this idea from reading Noakes's theory of light the other day that even since Newton's time, there's not just like the spectrum of the rainbow, Roy G. Biv, which is great, and not just at the ends that there's oscillation with regards to like the three kinds of violet, indigo, and purple, and these kinds of things, and red, and red. Then there's also the ideas that then those come up out of the primary colors in these secondary spectrums. Light has a secondary spectrum. Light is optical light is special in this way, yet it also reflects continuum mechanics as of mathematically. The book comes to a close with a brief chapter on the numerical solution of trajectory problems. One of the concepts here is that there's the geodesy, is basically the idea is like everything goes in a straight line. And that then for the theory of relativity, one of the premier theories of the day, it's so that then this geodesy is like, well, that's the curvature of space-time that arrives at these are the straight lines. And in what way is gravity, Einstein? It's straight down. And what way does anything go in the geodesy? It goes straight ahead. And so then the idea of the trajectifold and the orbifold is like, well, another great straight way of looking at that is that everything is in orbits all the time. And so that reflects on Kepler and reflects on all these different things that would still be so. And then with regards to like, well, how do you keep light going in the direction it is measured and observed to go, or at least not more than half off in these extremes in the fringes? And that is the orbifold more than the geodesy. That results that the geodesy is the same classical thing in the center, but the geodesy is always instantaneously evaluated. It changes through the whole universe at every instant of time. So it just goes to show that it's another way to realize that the usual notion that when you have a formula and have an equation in the middle, it's got all its implicits on either side, and that are held together there by the equals bar, and that or the other operator in a sense that it is. And then at the same time, all the unlinear is this whole theory of the sum of potentials, which really does define it. And then that last trace inside, what is the classical exposition, the classical account, the formula, is yet just another tangential inner product that is a result also of all the things that comprise it. The potential. It's a potential, and it's an equilibrium at equilibrium going to equilibrium, which changes. So that is inspired by this parasitic spectrum, which will be studied a bit here. One may well ask why it is necessary to add another treatise on differential equations to the many excellent textbooks which are already on the market. It is the author's contention, however, that neither the treatment nor the selection of the material duplicates any of the standard treatises. Points are stressed which often find scanty attention, while large fields are neglected which take a prominent part in other treatments. The emphasis is constantly on the one question: what are the basic and characteristic properties of linear differential operators? So, and he gets into Bessel, the Laguerre polynomials, local and global interpolations. So up after trapezoid rule, he starts with something pretty heavyweight like Taylor expansion, and then he gets into interpolation, the remainder of Lagrangian interpolation formula. There's Euler, there's Newton's, Gregory, and this and that. Coates. Coates was one of the great differential geometers before it was called differential geometry. So in the time of Newton, Coates was responsible for more methods of mathematical analysis than Newton. So kind of like, well, if you want to learn calculus, Newton's calculus, study Maclaurin. If you want to learn numerical methods and various things to do kind of attached to the logarithmic, there's Gregory. And then if you want to find out more about numerical methods and differential geometry, to Coates, C-O-A-T-E-S, Coates. And then binomial expansions, and that being like, well, from either side we can make the convolutive because we know when we multiply two monomials together that it starts building the coefficients in the middle. Or in the case when that's less than one and the products go outside, that inverts and flips. All in the middle, that gets into the whole ideas of the arithmetic, geometric, and harmonic means, as with regards to the usual theorem that there's always a strict ordering of those about when they're equal and about even when they do oscillate, when the impulses that would be in the system resonate and carry through, that they make these aspects of the motion and this kind of thing. The Laplace transform, the Stirling expansion, operations with the Stirling functions. So I'd be curious what he calls the Stirling functions, because usually the binomial function is like n choose k. And then there's n subset k and n cycle k, which are the Stirling numbers. So I'll be curious to see what he says are the Stirling functions. Then we're talking about the Bessel functions. Again, very closely related with the polynomials, the monomials, the binomials, and then also the convolutive setting. And then also with regards to the trigonometric and hyperbolic trigonometric. That sounded like a pretty wide grab bag of things. Yet at the same time, it's like because they all are in the same space. Harmonic analysis then is that section 2, as you mentioned. Matrix calc section 3, and then 4 is the function space. 5 is the Green's function about the role of the adjoint equation. Sturm-Liouville and parameterizations and weights into Green's, Riccati. More about Bessel and the hypergeometric series. Jump conditions for the transition exponential periodic. Jump conditions for the transition periodic exponential. See, these are cool things with regards to describe the description of all the things. The ultra-spherical polynomials, Sturm-Liouville, boundary value problems, numerical solutions of trajectory problems, the method of Gaussian quadrature, very de rigueur, global integration by Chebyshev polynomials, the method of global correction. These are kind of the ideas. A universal approach to the theory of boundary value problems. Page 508. We have traveled a long way since the beginning of this chapter and encountered many strange phenomena on our journey. In retrospection, we will summarize our findings. We've seen the method of separation of variables as an eminently useful tool for the solution of some particularly interesting differential equations if the boundary is of sufficient regularity. For the general understanding of the basic properties of boundary value problems, however, another approach was more powerful, which made use of an auxiliary function of considerable generality. This function had to satisfy the given inhomogeneous boundary conditions, but it was otherwise free of constraints. Hence, the differential equation remains unsatisfied, but the function performed the program of transforming the originally given homogeneous differential equation with inhomogeneous boundary conditions into an inhomogeneous differential equation with the homogeneous boundary conditions. So this was read from Duhamel's principle last time. This was picked up as that's part of Duhamel's principle and so Lanczos is saying that that's an important method of universal generality, which here is the idea of the idea that it's not just differential and not just integral, it's integrodiffer and differintegro, is this more abstract generality, is the idea. To this problem, we could apply directly the usual analysis. These conditions can be replaced by this completeness relation. And it sets up kind of like, instead of an orthogonality where it's like in the inside that they're set up, it's an integral of these two equations, one parameterized in terms of each other, and then he says, and the zero axes are omitted. So that would be like the envelope. These things that would otherwise possibly be intractable or have to be solved by this identity dimension original analysis, which is the way it is. While the given function, beta x, need not be orthogonal to the axes, the mu prime or u primes of i's x, of the parasitic spectrum, it is necessary that the projections in the direction of these axes shall be sufficiently weak to make the following sum convergent. Then he describes an inequality, or that this sum is convergent, that the infinite sum of the beta prime i's over the lambda prime i's, that's squared, so a quadrature or nil square of the functions over these eigenvalues is finite. Beyond this condition, which is necessary but not always sufficient, we have to demand the pointwise convergence of this infinite sum of the v prime at x of this, and so it employs thusly the idea of the usual sorts of analysis of infinite expressions and their truncations, and then to establish guarantees of convergence off that. In this general theory, we have moved far from the restricted class of well-posed problems which forbid the eigenvalue 0 with respect to both V and U spaces and forbid also the parasitic spectrum. Hence, it is of interest to see that even in the worst ill-posed problems, we are in fact not far from a well-posed problem, because a small but finite perturbation transforms all ill-posed problems into the well-posed category. And he says, as long as the operators line up. The operator on the left side has exactly the same eigenfunction as the original one, but the eigenvalues are shifted by a small amount. The shift eliminates the zero eigenvalue and also its immediate neighborhood, that is the parasitic spectrum. So sometimes that would be the symplectic analysis and the meromorphic, which is a way to compute analysis over the symmetries, because whenever there's a saddle point or anything that where it's not defined what direction is gradient descent, because it could be coming from any of a given number of directions, and they would each have different solutions, where it would be ill-posed to have it so that the gradient descent exists without establishing a wider principal component analysis. That here the meromorphic and symplectic kind of attain to those things, and then for Lanczos, then he just wants a linear differential operator, and so he's set that up that he just has a displacement, or from a different perspective, at least. We now have a complete and unconstrained operator, which satisfies all the requirements of a well-posed problem. The solution is unique. The right side beta x is not subjected to compatibility conditions. And the solution is not infinitely sensitive to small changes of the data. Green's function exists, and we can find the solution in the usual fashion with the help of this function. So this goes to show that there's the idea of the Poincare completion is that, hey, in this continuous domain, even there's still arbitrarily like everywhere singular type of ideas that would make it so it's like there's at least one intractable problem. Yet here Lanczos describes it via usual these means of transliteration of a sense of the coordinates, that it could be written up as long as these other conditions are said to so hold, then these results are said to so hold. Yet then, as has been discussed here many times, that the ideas of convergence and later emergence, because there are true facts of laws of large numbers that are multiple, then any singularity theory is a multiplicity theory, that this is otherwise a pretty great little conclusion of Lanczos. And then he gets in the numerical solution of trajectory problems. The rapid and spectacular development of the large electronic computers provided a new and powerful tool for the solution of problems which before have to be left unsolved. And that's kind of the issue today, is that everything's like, well, what can we do with this computer? It's like, well, you can give it, as long as you can frame it in terms of one of these linear differential equations, then it will solve it, which would take a person with a piece of paper an arbitrarily large amount of time, or on the order of lifetimes. It can solve it. But then the idea is that, well, we have some problems that's great, and so the whole school is like, learn linear differential analysis and then learn these numerical methods, and that's how you can learn how to get a lot done with the help of a computer. Because otherwise, it's like, if you didn't have like a giant supercomputer crunching numbers, then you could still figure it out, but it involves algebraic geometry more so than algebraic geometry in a sense. Is with regards to those, like the differential and integral, those having to go together, and it's really kind of crab clawed and asymmetrical, and there's a lot of under definition on what should be symmetrical and balanced. That this kind of thing comes up usually. The physicist and the construction engineer face frequently the situation that they need a numerical solution, which is not simple enough to allow a purely analytic solution. Still, we can get closer, and then it will be better. And then he talks about differential equations in normal form. We read these kind of from the university texts, and in C, and about the wave mechanics and the notions of ODEs from kind of this same time and place, 1960. And then he gets into more methods and estimations. Estimation of the error term, of course, is how methods are arrived at their quality, in a sense, their goodness of fit, their resistance to failure modes. So there's much to be gleaned from Lanczos setting up all these cool rules in linear differential equations, and then as with regards to then when they're kind of kept together some ways, because then it's to support the complex analysis, which is where the failure modes kind of are worse, and that's the big question of analyticity. It's like, is it still good? Is it still analytical, or vis-a-vis these algebraic manipulations that anybody could apply? It's like, and is with regards to all the implicits that go into establishing that something is well posed. It is so. And he gets into symmetries, the adjoint, convolutive, let's see, more about curl and the inner product and the convolutive and the reciprocating. The bilinear. Atomize, no matter how many independent variables we had, as soon as we begin to tabulate, we automatically begin to atomize the continuum. And by this process, we can line up any number of dimensions as a one-dimensional sequence of values. See, that's very much about this, the ideas of the continuum analysis and these laws of large numbers, that the real mechanics of these continuum mechanics are defined as with regards to these things. He establishes outline of some qualities. Show that the following properties of a matrix are the invariants of an arbitrary rotation, orthogonal transformation. A, symmetry. B, antisymmetry. C, orthogonality. D, the matrices 0 and 1. And E, or identity. And E, the scalar product x, y of two vectors. And so these are usually kind of like after linear superposition and linear independence, then these are kind of the fundamental aspects of linear analysis quite altogether. And then what it has to do is with the spaces, because a vector space, as being so defined and derived by these properties more than less, still has it so that things like torsion and whatnot have it that these do not include the affine. These merely define the notions that there's only a fixed number of perspectives. And so when there's the infinite dimensional, which there is, then this is kind of so that in an arbitrary rotation is as is mentioned, is kind of as of those fixed or finitely many. Which is great, it's just not complete. Mentions a paradox. The paradox, but the particular paradox holds that although eta n of x converges to 0 with increasing n at all points of the range, its equidistant interpolation boosts up the amplitudes of oscillations to such an extent that they go to infinity on the periphery of the range. The paradox. Well, see, this can be seen as a paradox. It can also be seen as just a continuity condition. So Lanczos' book here is pretty great, and of course it's famous, and it's reprinted all over the place. Or at least that is the exact identical edition that was so arrived at. Let's see, sound system engineering. Now this is not so relevant. We'll put this down for a second. Otherwise, also here's this something to be looked at a little bit. Fundamentals of astrophysics. Now sound engineering, has that. The overtone and these kinds of aspects of resonance theory, of course, are very much so part and parcel of this same sort of account of that. The usual accounts of the harmonic analysis in this way are, although forward and inductive, not complete. So this fundamentals of astrodynamics intends to talk about the geodesy and the orbifold and the trajectifold. The study of astrodynamics has become a common prerequisite for any engineer or scientist who expects to be involved in the aerospace sciences, and there are many applications. Talking about 1959, copyright 1971. Fundamentals of Astrodynamics is a new work, first published in 1971 by Dover Publications. So, this is talking about 1959. Classical orbital elements, determining the orbital elements, coordinate transformations, orbit determinations, SCZ to IGK transformation using ellipsoid Earth model, measurement of time, orbit determination from optical sightings, orbital maneuvers, orbit determination, ballistic missile trajectories, lunar trajectories, interplanetary trajectories. So the orbifold and trajectifold helps to define these things with the tendencies and propensities, that everything just goes in its orbit, that's its tendency, and then any changes are propensities. Those are trajectories. Miscellaneous constants and conversions. Page 430, vector review. Astrodynamic constants. So on page 429, it suggests the astrodynamic constants. The mean equatorial radius is 1 du 3963 miles, or 3963.195563. The time unit is 13.44686457 minutes. And the speed unit is one of those equatorial radiuses over the time unit, and it's 7.905368828 kilometers per second. Seconds per meter or meters per second. The gravitational parameter, angular rotation, and then that was the geocentric, and then the heliocentric. And these are derived from those values of mu, r, and au, and use at the NORAD USAF Space Defense Center 1975. Each of the two sets is consistent with itself, not necessarily with each other. See? Miscellaneous constants and conversions. And then a review of vector analysis. So in this book, there's plenty of differentiation because it defines, for moment in motion, it defines that the instantaneous rate of change or the area so measured by these things are in terms of the differential and the integral. And that differentiation and integration are the usual operations that can be applied to functions. You can so arrive at these variously. It is the most usual aspect of continuum analysis to find out what something is at a point in time. Then the things to do with space contraction and continuum analysis in the greater premier theory is it gets into these ideas like the orbifold and the trajectifold for the geodesy and these kinds of things. Bit of history. Cowell's method. This is the simplest and most straightforward of all the perturbation methods. It was developed by P.H. Cowell in the early 20th century and is used to determine the orbit of the 8th satellite of Jupiter. Cowell and Crommelin also used it to predict the return of Halley's Comet. This method has been rediscovered many times in many forms. It is especially popular and useful now with faster and larger capacity computers. The application of Cowell's method is simply to write the equations of motion of the object being studied, including all the perturbations, and then integrate them step by step numerically. Yeah, that would well be said to be like often rediscovered because that's all finite and element analysis is. So it becomes tractable with the help of computers, but without computers it is not tractable. Without having this lever that arrives at, somehow it's like a million miles long, it's got a fulcrum far away, and it won't bend. It's like but it won't bend in any other way either. That it helps go in things. In the 18th century, lunar theory was developed analytically by Euler, Clairaut, D'Alembert, Lagrange, and Laplace. And so here there's a discussion that that original analysis and the identity dimension bit is very, very closely related with the linear fractional equation and with Clairaut's equations and D'Alembert's equations, the integral equations. Geometry, ellipse geometry. Radar measurements. References. Albert Einstein, Introduction to Johannes Kepler. Einstein wrote an Introduction to Johannes Kepler. The three-body problem. Mémoire sur le problème des trois corps. Completely general closed-form solution for coordinates and partial derivatives of the two-body problem by W.H. Goodyear. A universal formulation for conic trajectories, basic variables and relationships by W.W. Lemon and J.E. Brooks. 1965. K. Stumpf, Neue Formeln and Hilfstafeln zur ephemeriden Rechnung. Computation of Keplerian conic sections. And so this is a book that is much for kind of somebody who's looking to compute an ephemeris or establish what is ongoing with these things since Kepler, the Hohmann transfer, and establishing which are some. This would be an example of something that crosses a boundary, and that otherwise it's like, well, on this side it's well defined, on that side it's well defined, but in terms of how it crosses that boundary, then it's not well defined. So there's various ways to establish that with the relations. Transfer between two circular coplanar orbits is one of the most useful maneuvers we have. The least speed change required for a transfer is achieved by using such a doubly tangent transfer ellipse. And so that just gets into when they're algebraic derivations that would go off the course and there are algebraic derivations that would not. And so the usual general means would go off the course, and then these things need to be put back together. So getting back into the integrodiffer and differintegro, let's kind of leaf through some more of these books while there's not much time so much relating. The Art of Modeling Dynamical Systems, Forecasting for Chaos, Randomness, and Determinism by Foster Morrison is a book that was printed by Wiley Inner Science in 1991. And so dynamical modeling, this is when, if a chaos theory was like, what's chaos theory? Is like our solutions are coming up with things that are not cool. And so we're going to call it chaos because this emergence is not matching our ideas of convergence and it's chaos. And chaos means anarchy and it's bad. It means that there's no explanations of things. And so we're going to call it chaos theory. And it's like, well, how's that going today? It's like, well, now we just call all that dynamical modeling because at least some of those things have kind of been fixed up. But it's still going to take like a theory with all these laws of large numbers to establish why the convergence criteria don't all contradict each other. And that otherwise there can be kind of a reasoned emergence phenomenon. The book is designed to fill a niche that rarely exists in scientific and technical publishing. Most books and articles in these fields are either highly technical and readable only by specialists or rather shallow popularizations. Much of the technical literature is difficult to read even for scientists and engineers. Even the best books tend to dwell on the mathematical models and don't give the slightest hint what to do if one is lucky enough to have some data. And he says, our style of presentation is discussion with examples and analogies and very deliberately avoids the definition, theorem, proof format. The emphasis is on exposition and a unifying concept is introduced in the hierarchy of dynamic systems. Let's take a look at that. The hierarchy of dynamic systems. Because the integrodiffer and differintegro, of course, that's what dynamical systems are all about, is systems in time that change in time and are functions of their own values with regards to the implicits and the exponential. Usually being the exponential is the only well-known formula that's kind of elementary that is known to be its own antiderivative and derivative. Then there's also one that's central down in continuity definition. The natural unit equivalency function is kind of a funny function. It's got real analytical character, yet it's also its own derivative and antiderivative. And it's a PDF, and it's a CDF, and it's otherwise of non-standard things. Yet it's real analytical character. So let's see if we can find this the hierarchy of dynamical systems. A summary of the scheme, page 166. Actual dynamic systems require a descriptive terminology to classify them. We consider the examples of random and stationary. Neither of these terms can be defined precisely in a mathematical way, but they are essential concepts for characterizing both observed systems and mathematical models. Later we shall add chaotic. Dynamical mathematical models, as well as actual systems, are so complex and diverse that they also require heuristic terminology. So that's just the kind of the wider descriptive. And then trying to figure out how to have the meeting in the middle of things that their completions attain to each other, but by induction they don't. That starts with just super classical reasoning about Zeno's propositions that resolve the paradoxes of motion by the infinite divisibility of time, which is kind of seen as a better way to see that than as like it's a paradox and now stop thinking it and nobody can ever figure it out, which would be wrong because it happens all the time. And it's natural, it's real, it's rational, and it's reasonable. This is getting into saying in our ontology of all these different systems, any one of which may be, then it gets descriptive. And there's sometimes the descriptions in their deconstructive accounts, the pseudo elements or the degenerate elements of those that can't build back together the same inductive accounts can be made structurally so that they arrive at yet this kind of some wider, fuller dialectic structural account. Dynamical mathematical models, much of the application is to actual systems, not models. So a completely rigorous system will never be possible. Now, systems is very wide. It means anything. It means anything that's related to anything else. And so where we have pretty much the theory already includes all the things, and then as it's a model theory as any structure at all, that kind of includes this definition of systems. But system does mean, for a mathematical model, as just being like a few constituent relating equations or formulas, and a system can be like inputs and outputs, or basically any kind of factor or aspect of the overall analysis at all. Anything that's part of the ansatz, the setup, the problem, the definition of then what's again just a model. Because in the model theory and proof theory, they're this equi-interpretable, that the model exists and that we have a proof that it's so, are the same thing in terms of what they intend to purport, how they can be approached from various model theoretic and proof theoretic accounts. Here kind of then the theory of systems, which is kind of after operations research, and it's like it's systems based, everything. Kind of like object-oriented analysis and programming is systems-based things in these dynamical models. So when we say dynamical models, we mean systems of things, and so dynamical models and systems of systems and open and closed systems. It's an open system, and then with regards to things like proofs and the proof machinery and the theory overall, it's all kind of one thing, but they're descriptive about each other in terms of each other's terms. Much of the application is to actual systems, not models, so a completely rigorous system will never be possible. The idea that it's an open system vis-a-vis a closed system has that closed system is like a closed category, and it's also like conserved and contained in these kinds of things with regards to symmetry and invariance and continuity and conservation laws. And then the open is that it's like it's not, and so that usually gets into like there's always something attenuating to the floor that makes it open, and physics is considered altogether an open system, and then altogether on the outside, open and closed at the same time. Yet that's because we're talking about universals beyond particulars here. Always remember that one can say some things about a model with absolute certainty because it is a mathematical construction subject to the algebraic derivations and these deconstructive accounts underneath it that like make it like, are you really sure that's a mathematical construction, the only one, or is it besides being a mathematical construction, is it the only structure? There's more structure is what I'm saying, because it is but there's never a sure thing in the real world. There is, but that's not saying our theories can figure it out. Mathematics can tell us things only about models and rarely ever enough about them. So he says, going on, perfectly good models can have mathematical properties that are meaningless, such as infinite divisibility into ever smaller pieces. See, for him to say something like that is meaningless, that's exactly what arrives at these different models of Cantor space, different models of continuous domains, different models of large numbers, and all these kinds of things. That's exactly what this modern superstandard analysis is. Yet here it's like when everything can be kept finite and inductive, that's very much kind of indisputable in itself. It can be internally self-consistent. You can still show it's wrong from the outside, and so that's just the usual course here. So he says there are 5 types in the hierarchy of dynamic systems, Morrison's, numbered 0, 1, 2, 3, and 4. At this stage, let's give just a brief description of them. Type 0 has no dynamics. Its state remains unchanged. Null operator. Type 1 is comprised of solvable systems. According to mathematical theory, all reasonable differential equations have solutions. By solvable, we mean that these solutions can be expressed in one of several ways. So, and so this might be solvable by means of ordinary differential analysis, because the author might not be including any other thing that may solve otherwise the thing. Problems that can be solved by perturbation techniques are placed in type 2. So this is differential equations largely. Type 3 have chaotic solutions. A typical trajectory may seem to be behaving normally and then execute a sudden change, of course. So these would include things part of resonance theory. The only resonance theory explains. Excuse me. Type 4 systems are random. And so that, to say that so, it's kind of like when we're talking about the modularity and whether it's the real and continuous or the integral and discrete, and whether one of those is the foundation from which the other one can be derived at, has it so that having the random as being type 4 is actually the random stochastic is that's just part and parcel of there being, sampling and observations. Any measurements or values arrived at are just at best scientific numbers according to measurement, sampling, and observation. So that there's always kind of the random, the ergodic, the emergent, for convenience. And so that just gives him kind of a hierarchy system. And then he has a kind of between 100% deterministic and 100% stochastic. So his kind of hierarchy kind of grows in rank or order, yet it's really just kind of this flip sides, whether it's deterministic or whether it's stochastic. So, but this has got a lot of stuff going on, and like a lot of stuff in dynamical modeling and systems theory, it looks to attach all these different kinds of means, and then it helps us just like from reading that thing about the asteroid dynamics. Then it's like there's all these pathways and styles and routine, and style in the sense of a crossing between two fields is a little ladder. It's called the stile, not the style, but in styles and styles. So. Well, gentle readers, that's been kind of differential dynamics today. And Logos 2000, the integrodiffer and differintegro. Here's the level I can run. Tensors, differential forms, and variational principles. Borisenko and Tarapov, vector and tensor analysis with applications. And then Lebedev, special functions and their applications. So this is a little bit beyond the elementary functions and gets into stuff like the gamma function, the factorial. The Dirichlet problem for a sphere. Describing potentials, the hypergeometric series and its analytic continuation. Describing the usual sort of Gaussian approach to the hypergeometric. There are others. Hypergeometric kind of just has the 0, 1, and infinity, or regular singular points of it, and it includes a point at infinity. So, and that it converges for z less than 1 and diverges for z greater than 1. That then reading this Lebedev's on special functions gets into some of these higher order constructs while yet maintaining a very, very delineated structural account of what can go into that. The Dirichlet problem for a parabolic cylinder. And his bibliography includes H. Bateman. Bateman is one of the great differential geometers. This says it's from 1959 was when it's printed. But like back in like 20, 30 years before that, that's one of the great surveys of differential analysis was read here one time. Erdelier, Hobson, Lenza, among many others. Trichomy, I'm not quite sure how that's pronounced. Gigot, orthogonal polynomials. Sternberg and Smith, the theory of potential and spherical harmonics. Whitaker. So these are just books after the tensor analysis and the tensor calculus. These are books in differential analysis. Tensor analysis on manifolds, Bishop and Samuel Goldberg. Tensor analysis for physicists, J.A. Schooten. This would probably be the most familiar for its place in the stacks. 1959, 1954, 1951. This second edition does not differ radically from the first. This book grew from lectures delivered before and during the war at Delft and at Amsterdam. The salient points of the theory: modern tensor calculus, modern problems of elasticity and piezoelectricity, and these affect also the vibrations and resonance and vibrations, oscillations as vis-a-vis these things. Geometric objects, yes, quite everything is geometric, say. They're just kind of, figuring out that this is kind of like the available stuff. Then this is Helmholtz on finite dimensional vector spaces. And then there's also Helmholtz on infinite dimensional vector spaces. So it's something to get figured out that somewhere in the stacks, and I'll be looking to dig it up a bit, is the infinite dimensional vector spaces. So as mentioned, this is also from D. Van Nostrand. And he says, the purpose of the book is to treat linear transformations on finite dimensional vector spaces by the methods of more general theories. So that helps to go, like people say, it's like, well, have you read Helmholtz's book? It's like, I know what it's called. What's it about? It's like, well, that's a good question, But then he gets into saying, but here, as he said, it's like there's like these integral analysis instead of differential analysis or whatever works, just a style that is in effect. The idea is to emphasize the simple geometric notions common to many parts of mathematics and applications, and to do so in a language that gives away the trade secrets and tells the student what's in the back of the minds of people proving theorems about integral equations and Hilbert spaces. So here he said integral equations, so now it's great. Well, all right, gentle readers, I shall so hope you have a great day today. March 23rd, 2025. And that all is well with you and yours, and that the weather about the weather this year, how that's going to be.